Hi everyone, in this video I'd like to show an example of how to find extrema for a given function. And I'm going to be looking at f of x equals the cube root of x. And that's a little bit hard to work with, so I'm just going to rewrite this as x to the 1/3 power. Now I can apply the power rule to finding the derivative for that. So that's good. Okay, so we're going to be working with 4 steps. The first step is to find the domain of the function. So that sort of x values I can stuff into this function, the sort of x values I can take f of x are really all real numbers, because I can take the cube root of negative numbers, like -8, cube root of -8 is -2. So all real numbers are permitted here. So the domain is going to be -infinity up to infinity. You could say all real numbers. You could say -infinity less than x less than infinity. A lot of ways to express the domain. Okay, for the first derivative and the critical values, we're going to apply the power rule. The first derivative here would be 1/3 x to the -2/3 power. And I need to set that equal to 0 and undefined. Now again, that exponent there is a little bit hard to work with. It's a little bit hard to see, when is this going to be equal to 0 and so forth. So I'm going to rewrite this as, let's see, 1/3. I've got a 1 up there in the numerator, and down in the denominator, I've got 3. There's my 1/3. And x to the -2/3 power means that x to the 2/3 is going to be down here in the denominator. I've got a cube root of x squared. All right, so that's a little bit easier to see. Now, if we try to set this puppy equal to 0, there's going to be no solution. There's no way that first derivative is equal to 0. I've got a 1 up there in the numerator, so that doesn't yield anything. Now, if I look at when is f prime of x undefined, when would that happen? Well, if we have a 0 down there in the denominator, that will make this fraction undefined. So x equals 0 is when the derivative is going to be undefined. I can make a conclusion here and say the critical values, I'll just abbreviate that, critical value occurs when x equals 0. And you could plug in and find the y value. You could say y equals 0 as well. It's going to be right at the origin. Okay, that's very good. So we've got 2 pieces of information so far. We've got our domain, we've got our critical value. We're on to step 3. So for step 3, we want to find the second derivative. So let's do that. I'm going to be working with my power rule again. So bringing that -2/3 down in front, I've got a -2/9 x to the negative, I'm subtracting 3/3 off the back end there, so that's -5/3. Writing that as a fraction, I've got a -2 up in the numerator, 9 in the denominator, cube root of x to the 5th power. And again, I'm going to go through the same exercise of saying, hey, when is that second derivative equal to 0? Well, that's not going to happen. And when is it going to be undefined? That happens when x equals 0. And at this point, we have a possible inflection point. We don't know if it's actually an inflection point. Recall that inflection points, so I'll just write this down as a reminder, inflection points are places where the concavity changes. It's not enough to just say that the second derivative was 0 or undefined. That is true when we're looking at critical values. It's enough to just say, oh, it was 0 or undefined. But if we're looking at inflection points, we have to really go in and test if the concavity changes or not. So this is a possible inflection point, and I won't really know if it's an inflection point until I get down here to step 4. So I'm going to label this as a possible IP, possible inflection point, and that's also at x equals 0. Okay, so let's take a look at step 4. This is where we make a sign chart. And for my sign chart, Down here at the bottom, I'm going to list x values. And the only interesting x value in town is x equals 0. If you had other possible inflection points or other critical values, you'd put them down here on your number line as well. And then my number line goes in both directions, to infinity, because that's my domain. So I'm not going to put a stopping point on either end of that. And then the next row up, I'm going to put my first derivative and then my second derivative. And let's go in and see what happens here. So when x equals 0, I know the first derivative is undefined. Now, for values that are less than 0, I don't care, -1 would be a good test value. What happens when x is -1? In other words, what is the sign of the derivative when x equals -1? If we go back up here and look, 1/3 cubed root of -1 squared. What does that look like? Well, it looks like that's always going to be positive. Similarly, if we put that was greater than 0, if we look at some test value on the other side, I don't care, you could look at 8, you could look at 1, whatever you want to look at, and if you go through and analyze that, that's also going to be positive. So what this means is that our slope, or our derivative, that is always positive. My function is going uphill. It's always increasing. So I've got an always increasing function. And I'll write that down in a minute. Next, for the second derivative, let's go in and analyze that. I'll just choose a different color so you can see what I'm up to here. The second derivative is undefined at x equals 0. And if we plug in a value over here, like -1, let's see, I've got -2/9 cube root of -1. So that's going to be -2/9. That turns out to be positive. And again, if you plug in something on the other side, I'll just make my life easy. No need to work with an 8 if I can work with a 1. And that turns out to be negative. So if you go through the calculation there. So indeed, I do have a confirmed inflection point. It's good we tested it because sometimes you won't have an inflection point, but you do have to go through and test it. So if I were interested in graphing, what does this function look like? Well, my function is going uphill. So I know it's going uphill. I'm always going uphill. And here I'm concave up like a smile, and here I'm concave down like a frown. So if I were to try to draw a function that was going uphill and concave up, there we go. And then I hit an inflection point and I'm still going uphill, but I'm concave down. So it kind of looks like this S-shaped curve. And if we were to attempt to draw that, use a different color. I know it passes through the origin when x is 0, y is 0. I know it goes on in both directions, doesn't stop because of my domain. And I know it's making this S shape. So it's going uphill, it's increasing, and it's concave up. I hit the origin. I'm still increasing, but now I've changed my concavity and I'm concave down. And so that would be my sketch.